Good evening everyone, my name is KSHITIJ Shankhwar and my enrollment number is BT23CME004 and my topic is flow over inclined flat plate. So first we will look over this question. This question says that consider the flow of a liquid down an inclined flat plate of length L and width W as shown in figure. The inclination angle of the plate is beta and the thickness of film over the plate is kept constant delta, with the reservoir at the top. If delta is very small as compared to length and width, derive the equation for velocity and momentum flux profile and hence develop the equation for maximum velocity, average velocity, mass flow rate and drag force on the plate. So we will solve this question by two methods. First is shell balance and second is equation of change. So this is the figure in which the reservoir have an inclination angle of beta and there is an entrance disturbance and an exit disturbance, and there is a film of liquid which is over a length L. So this is the Cartesian diagram of the above question. So we will take our coordinate system as Cartesian coordinate system, and we will take our origin at x is equal to x, y is equal to w and z is equal to 0. So we will take some assumptions is that the velocity in the x direction is 0, the velocity in the y direction is 0, and there is velocity only in z direction which is a function of x, and we have pressure which is also a function of. So as we have velocity only in z direction, we will take only z momentum balance. So the total rate of z momentum in across surface at x will be phi xz at x into L into W. Total rate of z momentum out across surface at x plus delta x will be phi xz at x plus delta x into L into W. Then we will have total rate of z momentum in across surface at y is equal to 0, that will be phi yz at y is equal to 0 into L into delta x. Then we have total rate of z momentum out across surface at phi is equal to W, that is phi yz at y is equal to W into L into delta x. Similarly, we will have across at z is equal to 0 and z is equal to L. Then we will have gravity force acting on the fluid in z direction, that will be rho into length into width into delta x into g into cos beta. And if we do complete shell momentum balance, we will have this equation, and then we will divide this equation by total volume and take the limit of delta x tending to 0, and we will use definition of derivative. Then we will have this equation d phi xz upon dx plus phi yz at y is equal to 0 minus phi yz at y is equal to w plus upon w plus phi xz at x at z is equal to L minus phi zz at z is equal to 0 by L is equal to rho g cos beta. We have the momentum flux components are written as phi xz is equal to tau xz plus rho vx vz. Similarly, we have for phi yz and phi zz. So now we will simplify our equation by eliminating some terms. Since velocity in the y direction is 0, the term rho vy vz in phi yz will be 0. Since velocity in z direction is a function of x, the term dvz by dy in phi yz is 0. Similarly, we will eliminate phi yz dvz by dz by using the relation of velocity in z direction is a function of x. So by eliminating our terms, we will get the final equation as d tau xz by dx is equal to rho g cos beta, and after we integrate it, we will get tau xz is equal to rho g cos beta x plus c1. We will use boundary condition 1 at x is equal to 0, tau xz is equal to 0, so c1 will be 0 and tau xz is equal to rho g cos beta x. Using Newton's law of viscosity, tau xz is equal to minus u dv z by dx, and when we substitute the Newton's law of viscosity, dvz by dx is equal to minus rho g cos beta by u into x. If we integrate it again, we will get the velocity profile, that is vz is equal to minus rho g cos beta upon 2u into x square plus c2. We will use boundary condition 2 to find the velocity profile. At x is equal to delta, vz is equal to 0. This After this, we will calculate the value of C2, which will be rho g cos beta upon 2u into del square. Final velocity distribution will be Vz is equal to rho g del square cos beta upon 2u in bracket 1 minus x by delta whole square. Then we will calculate maximum velocity, average velocity, mass flow rate and film thickness and force